we would like to thank and acknowledge our sponsors, DC3 Dreams and Boyce Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay, without any further ado, our first presenter for today is a senior research scientist at the NASA Ames Research Center, where he currently works on studying exoplanets. He's had an accomplished career, to say the least, from helping to pioneer the use of CCD cameras in astronomy to serving as project scientist for the NASA Kepler and K2 missions. Back in 2011, he and Dr. Travis Rector began an observing campaign with the AAVSO, requesting long-term monitoring of a selection of bright giant variables. Today, we are lucky enough to have him here with us to share some of the fascinating results from that project. Ladies and gentlemen, please give a warm welcome to Dr. Steve Howell.
Thank you, Lauren, and welcome to everyone. I guess it's good morning, evening, afternoon, and night. People seem to be all over the world. It's really great to see you all today. The AAVSO is probably my favorite astronomical organization. So I'm very honored to be giving this webinar today, and hopefully we'll have some fun mutual stuff that comes out of this with some more interesting research we can do. So you've all seen the title. I'd like to just move on here to, maybe I'll move on here. There we go. To a little bit of an outline of the talk. I want to give you a little bit of information on my motivation of why I want to study these particular stars, and also the motivation of why it's important that organizations like the AAVSO, in fact, particularly the AAVSO, is involved in this. A little bit of background in terms of how we will learn what we learned today, what we have learned about these stars. And also I want to talk about 3 case studies, the exciting science we've learned over the decades of this project. I thought it'd be fun to start with a little history of myself and the AAVSO, and I do this as a selected history. There are more things, but I was first introduced to the AAVSO as a teenage amateur astronomer back in the last century, around 1970. I'm not exactly sure of the date, but somewhere around that day. I then used a lot of AAVSO data in my graduate school studies, which were primarily about variability of objects that were very faint. So they got bright at times, but they were mostly faint. As Lauren mentioned, we started getting very interested, or I started getting very interested in the stars we'll talk about today, these objects called semi-regular variables, also in graduate school around 1982. And I'll show you why I got very interested in them and what I think we can learn from them. She mentioned the collaboration with the AAVSO on semi-regular variables. I also had a long-term collaboration with AAVSO observers on cataclysmic variables. And those have run for decades, and there's a lot to be said about studying objects for decades in our very short human existence. That's a pretty long time to study some stars. I also list here the 3 directors of the AAVSO that I've known and worked with. So thanks to all of you for helping me get these collaborations going and having your members do so much great work. So I'm going to celebrate myself here with 50 years of being with the AAVSO. Thank you for that. A great time. All right, so let's start with a little bit of background information, a little bit of motivation. So in this particular diagram, this is called a Hertzsprung-Russell diagram. And it's sort of a fundamental, easy way to learn things about stars. And the numbers on here, for those of you who don't know, are just units that scientists use. But The thing to keep in mind here is that if you go from left to right in this diagram, stars go from being very hot to being very cool. Our sun, you can kind of see our sun is here in the middle, sort of an average star, at a surface temperature of about 6,000 degrees. Stars get very hot, very cold. And if you go from the bottom of this diagram to the top of this diagram, stars get intrinsically brighter. That is, if I took a star at the bottom of this diagram and I took a star at the top of this diagram and put them right beside each other at the same distance from me, the stars at the top of the diagram would be far, far brighter than the stars at the bottom of the diagram. But more importantly, this diagram can tell you about where a star is in its lifetime, and it can tell you about what sorts of periodicity and variability you should expect from that star. So if I bring up another diagram here, that's the same thing, but now it has some other lines on it. These colored lines show the movement of a star on this diagram, not the movement of the star in space, but where the stars move on this diagram when they start their life on this line in the middle called the main sequence. And that's where our sun is right now. It's kind of an average normal star doing its average normal thing. And then these stars will move along these colored lines as they get old and begin to die. So if I wanted to study, for example, the life cycle of an oak tree, I would get an acorn and I could plant the acorn and I could sit in a chair and I could stare at that tree growing for say 400 years and write down everything about that tree. And I would learn the history of that one tree. The problem is 400 years is kind of long for humans. So what I might do is I might look at acorns and then go study young oak trees and then go study middle-aged oak trees and then go study old oak trees. Of course, these are all different trees, but they're all the same kind of an oak tree. And then I would put together some idea of how the oak tree lives, grows, and dies. So we do the same thing with stars. We study stars of all ages and then try to piece together some model of how this star's life cycle works. And the interesting thing for me is if you look at this diagram on the left, all of these lines end up in that same sort of rectangular colored region up there. And that's the region that we're going to focus on today. That's the region where stars do things that are called semi-regular variability. And I'll show you some examples of that. But the important part for me about that particular place is that is the ends of the evolutions of all kind of normal stars. They do something dramatic after that. They explode or they blow off their entire atmosphere. They do something that recycles their material back into the universe to form new stars, to form new planets, and to form new life. So it's a very interesting time in the lifetime of stars. So just a little bit of background. We want to talk a little bit about what variability means for those of you that have never seen this or don't know what this is. I give some examples here of pictures of the sky. These are images of stars in the sky. And you can see on the left, there's a star that in one of those images is very bright, and the other image is very faint, almost invisible. So this is the same star, but the star changes its brightness over time with some regularity. And the thing down below, that graph down below, shows a measurement of such star where brightness is higher in the diagram and time goes from left to right. So if I watch that star, it would be faint, then it would get bright for a while, then it would get faint again, then it'd get bright for a while. And that star on the sky would keep changing its brightness due to certain things that are happening at that star. On the right side, I show 6 images of the same place in the sky. And if you look at the star in the middle of those images, you see that it too changes in brightness. In this case, it's not quite so dramatic. And again, below, I show a graph of this. We as scientists make graphs. And again, it's brightness increasing to the top of the diagram, time going from left to right. And here you can see this star does kind of a sawtooth pattern. It gets brighter and fainter and brighter and fainter, but it doesn't do it in the same way as the star on the left. So these are 2 examples of stars that have relatively periodic variation. And by understanding this variation, we can learn what's going on in these stars. So another example of those kinds of light curves, those are called light curves, sorry, the time and brightness. Here's just another set of them. One on the left is a pulsating star. It has a period of about 400 days. So it's a little over a year. And here you can see the star gets brighter and fainter, but it has this interesting every other time it's a little brighter and every other time it's a little fainter. So again, if you studied that star, that would be very helpful to learn something from it. And on the right, I show a set of, 16 of these measurements of light over time, these things we call light curves. And these are for eclipsing binaries. So these are actually pairs of stars that orbit around each other. They're gravitationally bound, orbit around each other. And at certain points in their orbit, one star goes right in front of the other star as viewed from the Earth, and it blocks the light of that star. And you can see those periodic dips in these light curves where one star is blocking the light from the other star. But you can see also that they don't all look the same. Every star doesn't block the same amount of light. Every shape of the brightness over time doesn't look the same. So again, by studying these kinds of stars, you can learn something about what's going on there at their particular places in their evolution. So here's the stars I want to talk about today, that I care about today. And these are things called semi-regular variables. On the left is a beautiful set of observations. I think it's about 90 years long. 90 years this star has been looked at by members of the AAVSO. And this, in fact, ends, I think this particular graph ends in 2000. So I'm sure there's another 20 years here. And it's brightness versus time. And each horizontal row is roughly a decade of time for that star. And you notice, especially near the bottom of this diagram, that there's dips, and they're not quite regular, but they're semi-regular. So something is happening in this star that causes these decreases in brightness, but it's not quite periodic. So this is not going to be an eclipsing binary. Those will be very periodic, but something's going on there, and we'll get to investigate, in fact, this exact star in just a moment to find out what's going on there. And on the right, I just show three other examples. Again, it's brightness going high in the diagram and time going from left to right. In this case, the units of time are days. And so over a few days here, something like 100 days or something, you can see these stars at times look like they're going to be periodic, but they're just not quite periodic. So we call them semi-regular. And so we want to learn what causes the variations here, and that will teach us something about the stars. I want to take another little aside here and talk about spectroscopy. So for some of you, this is probably well known, and for others of you, this is maybe something you're not so aware of, but we all have seen a spectrum before, a thing that scientists call a spectrum, and that's shown on the left here as a rainbow. And in this particular case, it's a bit of sunlight that gets spread into its colors by water droplets. So there are various ways you can spread light out. Maybe a prism is something that's more familiar to all of you, but you can also do it with things like water droplets. And we see a rainbow where we see all the colors of the rainbow, and they go from red to blue, you know, the Roy G. Biv kind of acronym here. And if you could see with your eyes, if you could see infrared light that's redder than the reddest light we can see with our eyes, and if you could see ultraviolet light that's purpler than the purple light, you would see that light is also spread out as well. It would make rainbows as well. You just can't see those with your eye, but other instruments that scientists use, that astronomers use, can detect that light. And on the right here, I want to show you another fascinating property about making rainbows or doing spectroscopy. If I take a pure sample of an element, for example, sodium, and I spread the light of sodium out by using some mechanism, it could be a prism, I see in the part of the spectrum where my eye can detect it, I see that single yellow feature. So I don't see all the colors of the rainbow, I just see that one color yellow. And if I do it for mercury, I see that array, that's the second line down there, I see that array of individual colors. So these are called spectral lines because they're linear. And I only see those particular lines if I have a pure sodium or pure mercury, and the bottom is pure hydrogen. So the interesting thing about that is every element has a unique set of these lines, much like a fingerprint. If I can detect these individual lines instead of that broad color of a rainbow, if I can detect these individual lines, I can match them to the element they belong to, and I can tell you what elements are in that star. So you might say, well, how come the rainbow doesn't have these lines, but these pure elements do have the lines? Well, that's because your eye just can't see them. But let me show you an example of if I take a spectrum of the sun, but I do it with an instrument that has better resolution than my eye. So now what I would see is I would see the colors of the rainbow. You see that at the bottom. I've now flipped the colors, so red's on the right, purple's on the left. But you can see that I see all the colors of the rainbow, but there are vertical lines in here, hundreds of vertical lines in here that are all those spectral features of a mixture of elements that are in the atmosphere of the sun. But this spectrum now has a resolution better than my eye, and so I now can see all of these features. So if I took a spectrum of the sun and I identified all those features, which by now has been done, but it wasn't an easy task, it took a long time, I can tell you what elements are in the sun's atmosphere. And in fact, if I watch the sun over time, over hundreds of millions of years or tens of millions of years, these elements would change. The amount of them would change. Some elements would completely disappear and other elements might appear. So the spectrum can tell us things if we can use resolutions to see all these lines. And that's what we're going to do. We're going to talk about photometry, where we measure the brightness of an object. And we're going to talk about spectroscopy, where we measure something about the composition and what exists in that. And the spectra we will see in the presentation here will look like the thing on the bottom here, the graph on the bottom, where, as we mentioned before, scientists like to make graphs. We like to plot something against something else. But keep in mind that when we see this, it's brightness going higher in the diagram, and it's just color along the bottom axis with blue on the left and red on the right. And the thing on the top is similar to what we saw before. It's sort of a long band of light with these black lines in it. And then on the bottom, we see all of those black lines make these dips in the spectra. So the dips in the spectra are important that we can figure out what elements are in that atmosphere. This is another famous, interesting variable star called Epsilon Aurigae, which we will not be talking about today, but it's a fascinating object. All right, so having said that, let's get on with the show. All right, so I first want to talk about a really lovely case. This is what really got me interested in semi-regular variables. And this was work that started when I was a graduate student and actually is still continuing today. So it's really a long-term side project, I should say. So on the left of this slide, I show a section, a small section of that 90-year history of the brightness of this particular star called R Scuti. So Scuti is because it's in the constellation Scutum, and the R is a designation astronomers use to designate variable stars. So these plots on the left are time going from left to right and brightness going from the bottom to the top. And the top section and the bottom section are just two sections of time. And you can see on there's two arrows, one on the top. I don't know if you can see my cursor, but there's an arrow up here and there's an arrow down here. And at the time of those two arrows were times when we observed that object with a spectrograph, an instrument on a telescope that produced a spectrum of light for us. And those are shown on the right side. And if you look at the right side top, you see what's a spectrum of this star in what's called the normal bright state, where it's up at the top of its brightness. It's as bright as it ever gets. And like we saw in the last slide, you see a bunch of those dips. Those dips all tell me about what elements are in that star and what those elements are doing in terms of what their temperature is and what the density of the material is that they sit in. There's also, if you notice, one line that sticks up there, and that's called an emission line. And that means that there's some very hot gas for that one element. In this case, it happens to be hydrogen that's producing emission. And we'll see where that comes from in a moment. But now if we go to the spectrum on the bottom, that spectrum on the bottom was taken at the very bottom of that low dip on the left side over there. So you see, it's a very different place in the brightness of this star. So the star was going along being bright, but now it fell very faint by 3 magnitudes, which is a factor of 70 or so in brightness. And now you can see that its spectrum now, covering the same area as above pretty much, is now very different in how it looks. There are no dips that go down anymore, but now there's a bunch of lines that stick up. And those tell me that something very different has happened to the physical nature of the surroundings, the atmosphere and the surroundings of that star. And in fact, if you use this information and build a model of what's happened, you find that the star went from this kind of a thing, just a star with sunspots on its surface, with a normal sort of spectrum of these lines that dip down, showing you materials in the star. And then when it fell into that very deep minimum, this is what happened to the star. The star blew off part of its atmosphere out into space. And when that originally was blown off, it hid the star from view. And so the star became fainter because this material, this gas and dust, actually hid the light coming from the star for a while as it expands out into space in a big expanding shell around that star. And all of these lines that stick up down here on the bottom, all these things called emission lines, are coming from that shell. They're not coming from the star at all. And they're telling me that that shell is made of very thin, hot gas, where in the first spectrum, those lines were coming from something that was very cold, dense gas in the atmosphere of the star. So the importance of the AAVSO light curve here, the importance of the photometry is these two spectra are so different. And if I didn't know something about what the brightness of that star was doing, the interpretation of these spectra would not be really possible. It would be very difficult to know what's going on. So let's move on to another case, another, I think, very interesting case. They're all interesting. I love stars. And so these are very fun because they don't work very nicely. They're not sort of like a periodic variable. Everyone's a little mystery story. It's just absolutely fascinating. Here's another long light curve of a star called R Coronae Borealis. Notice it's also called R, it just happens to be. This is in the constellation of Coronae Borealis, very cleverly named by astronomers. And here's its long-term light curve going from 1910 up to, I think this goes to about the year 2000. So again, it's 90 years of observations of this one star. And you can see over here, remember, every vertical row is a measurement of brightness going up in that vertical row and time going from left to right. So this star goes along spending a fair amount of its time being at its brightest level, but every once in a while it makes these very sharp dips. Some of them are very short, like in the second row. Some of them are very long, like in the fourth row up from the bottom. So interestingly, people want to study these stars like me, and you want to look at these stars at certain times because you want to know what's going on when it's bright and what's going on when it's faint and what happens to that star. So on the right, I just show a segment of a sort of blown up segment where you can see that the star here now has many, many little dips. If you start looking at it in great detail, this star actually dips quite a lot. And the bottom just shows a blow up of the very last dip that you see in the top row where it goes way down and back up. The bottom plot here shows a blow up of that where you can see how rapidly this star drops. Within a few days, this star can drop by factors of thousands in brightness. And then it stays down there at this bottom level being flat for a while and eventually comes back up to being bright. So what's going on here? What's causing this star to do this? If I can move on to the next slide. There we go. All right. So on the left, I've just repeated that measurement of its brightness that I showed you in the first slide. But now I've put arrows on this to show you when we observed that star, again, using spectroscopy and what that star looked like. And this star is one of the most fascinating astronomical spectra that anybody has probably ever seen or ever showed you. I would claim there is no other object that looks like this object when it's in its faint state. This is just an absolutely fascinating spectrum. So the first one at the top left, you can see it looks very messy. It looks like noise, but every one of those wiggles is a real spectral feature due to some element. So while that looks like noise, it's not noise. Those are all individual spectral lines of many tens of elements all mixed together in that spectrum. The other 5 spectra here that look like they show absolutely nothing but these 3 narrow bright lines, those are what this object looks like when it's in this very faint state, but it's in this very deep minimum state. And much like the star before this, all those lines don't really come from the star at all. Those lines come from a shell of material. In this case, they come from many shells of material that are around this star, each shell being the newest one in a succession of shell after shell after shell that's been blown off the atmosphere of this star as it goes through its dying phases of its stellar evolution. And if I look at these bright lines in some detail, I can actually see the individual shells out to some point from this star. So on the left is a little hand-drawn model of what I might be looking at. So I have that black dot in the middle, that black thing in the middle is the star. Around it is its atmosphere, the thing that we label over here called a chromosphere, but it's really the star's atmosphere and its outer atmosphere. And then A, B, and C are three shells, A being the one that was just blown off in the deep minimum, but B and C being shells that were blown off before and are all expanding away from the star. So it would look like a star in the center with spheres around it, many, many, many of them, each one getting less dense as it moves out and being harder and harder to see. But if I now look at these emission features, these bright lines, especially in the bottom plot here, and this is a subtle detail, but it's what you can learn if you have a light curve in spectroscopy, you can see in this bottom plot, each of these things, each of these little emission lines has three peaks. 1, 2, 3, 1, 2, 3, 1, 2, and you don't see the third one here. But each of those peaks is one of these shells. It tells you about the shells that are being blown away from this star. So if you watch this star over time and you took spectra of the star over time, you would see these shells being blown off and expanding away from the star. And each time it does that, it loses some mass, some material out into space. And that material goes out into space and helps form new stars and new everything else. So another really fascinating object is our Coronae Borealis. It's called a carbon star. It's one of the very odd parts in its resolution. I'm sorry, its evolution. All right, let me come to my third object here, probably my all-time favorite. Actually, there's two objects here, and they're both my all-time favorite. This is Merrill's iron star. Merrill was an astronomer in the early part of the 1900s. The star is better known as XX Ophiuchus. I just love the designation. Again, the XX is a way of designating a variable object, and Ophiuchus is the constellation this star happens to be in. And I show here on the left something that probably many of you have never seen. This is a spectrum taken in 1944 of XX Ophiuchus. And in 1944, there were no CCD detectors. There were photographic plates. So people used photographic plates to record images of the sky and to record spectroscopy. And this is a spectrum that Merrill took in 1944, where he wrote a scientific paper and said, this star has lots of lines that are showing a lot of emission, but from iron. So it has so many iron emission lines that he thought maybe this star somehow had this super concentration of iron, a super abundance of iron in its atmosphere through some odd mechanism. And indeed, that lasted for many years, that people believed there was something odd about this star, that it had a lot of iron in its atmosphere. On the right, I show you more recent spectra taken in 1998. These were now taken with a CCD detector, so they look like the kind of graphs that we've been seeing. And if you notice, nothing over here on the right has any dips that point down. The only possible one is down here in the bottom diagram. You see these two little symbols marking that dip and that dip, those two dips. Those are due to the Earth's atmosphere. Those are absorptions of materials in our atmosphere as the starlight passes through our atmosphere to my telescope. So otherwise, you see nothing but these bright features. The majority of them are due to iron. And that's just fascinating. No star has a spectrum like this. Well, as a graduate student and as a young astronomer, this was fascinating to me. And I decided to go look for more of these stars. And I found one more. And this star is called AS325. It probably has some other designation now, but I always know it as AS325. It turns out this star also is in the constellation Ophiuchus, very close in direction, not in space, but in direction to XX Ophiuchus. And it also shows a spectrum that has nothing essentially but these bright lines due to iron emission. So it looks like there's lots of iron, and somehow that iron is very hot, and iron is producing this big bunch of emission. And how can this be in a star? How can this work? Now, there's a little clue in this first spectrum on the left that I show you. So remember, on the left, the spectrum is blue on the left, red on the right. So it's just color moving from left to right and brightness moving from bottom to the top. And you see those two lines that dip down there that are marked K and H. Keep those in mind. Those are a real clue that we'll get to. On the right, I show you something interesting where I compare the bottom spectrum, which is not AS325. It's a normal giant star. And the spectrum right above it, the two in that green sort of box, that's the spectrum in this covering the same color range for AS325. And you can see how AS325 doesn't look at all like a normal giant star. A normal giant star has those big chunky lumps in it, which turn out to be due to features caused by molecules, in particular titanium oxide, that are in the atmosphere of that star. But we don't see those in AS325. Maybe we will. Hang on, keep that thought in mind too. So is this star, an XX Ophiuchus, a star that has a super iron abundance in its atmosphere somehow? Or is there some other reason for this? Well, AAVSO photometry comes to the rescue. And this is fascinating stuff that just really solved the mystery of both of these stars. It turns out we'll find out these stars are almost the same kinds of objects. So the top left shows again, a light curve. So it's brightness over time. Time goes from left to right. Brightness goes from the bottom to the top. And this is for the star XX Ophiuchus. And you can see what happens here. The light comes along and it gets a little dimmer and a little dimmer. And then all of a sudden there's this big U shape that happens. Well, it turns out that's an eclipse. So this object is going to end up being a binary star where one object in the system blocks the light from some other object in the system. The light curve on the bottom right here for AS325 is even more fascinating because here you see 5 eclipses, and probably a 6th one was in there but was missed because the object was behind the sun. It was up in the daytime, you couldn't see it. So you can see that AS325 also shows eclipses. It too is a binary star. So now we have 2 clues. We know they're binary stars. They both have lots of iron emission. What's going on? Just to point out for you observers out there, XX Ophiuchus has not yet shown another eclipse that I know of. Therefore, we don't quite know its orbital period. So hopefully you're continuing to look at it. We'll find that someday. In AS325, we can see here that the eclipses come fairly regularly, and you can count the time, look at the time between those eclipses, and find out its orbital period. So we did that with AS325. Its orbital period is about 513 days. So these are 2 stars that orbit around each other about every 2 years. And every time one of them passes in front of the other one, we see the light from that star drop because it blocks out some of the light. You can even go into more detail with photometry. Instead of just measuring the light, you can measure the light in each color. So you can measure the blue light, you can measure the yellow light, you can measure the green light, you can measure the red light, and you can look at all the ways those light change. And the blue light doesn't always change the same way that the red light changes because of various physical things that are going on in the star. And I show that on the bottom right here. That's the eclipse, the big deep eclipse in the top left. But now it's shown as 4 different colors on the same scale. So you see that the reddest of those colors in kind of the purpley points stays brighter, and the bluer points down there stay fainter. So there's something there that's a clue too, that's telling us what's going on by looking at how the light changes over time and with color. So now we're going to try to figure out what the 2 stars are in AS325, because we now know they're binaries. We saw the eclipses in the light curve. So we now want to try to figure out what the objects are, the 2 stars that are in them. So on the left here, I show what now should be very familiar to you. You've seen it 3 times, a spectrum of AS325 showing nothing but these iron emission lines, nothing but light coming from very hot iron atoms. There's no indication here of anything like a normal star. So how can I find either of the star components in this binary? Well, so what you do is you start looking at other wavelengths. If I look at the optical, where my eye can see, that's what I see on the left here. I see all these emission lines. But what happens if I look at this object in the ultraviolet, in light that's bluer than my eye can see? And in fact, in light that's so blue, I can only make this measurement if I have a telescope that is above the Earth's atmosphere, a telescope that's in orbit or outside the Earth's atmosphere. So on the bottom right are spectra we took of both AS325 and XX Ophiuchus and a normal B star. We took these spectra with the Hubble Space Telescope. It's above the Earth's atmosphere, so we can see the ultraviolet light. And you notice that now the three stars look fairly similar. So in the optical, XX Ophiuchus and AS325 look like these big, weird things of a bunch of iron emission, but now in the ultraviolet, they kind of all look similar to this star at the bottom that's a normal B star. So we've now figured out one of the stars in these systems is a B star because it has a spectrum that matches the wiggly lines with absorption features and that to B stars. So there's one clue. So there's a B star, there's nothing odd about it. So there's no extra iron in this B star. There's nothing going on in this B star that would make it seem any different than a regular B star. Huh, so now what do? Well, let's try to find the other star in this system. So what we did was we looked at the star when it was in a deep eclipse. So the spectrum on the top shows most of the optical bandpass. So this would be the spectrum you would see with your eye. And on the bottom, I've just zoomed in on a part of that spectrum that shows what we saw before, these big, giant, broad dip features that tell me that this star that I'm seeing with these big features is a very cool star. So in the ultraviolet, I noticed a very hot blue star called spectral type B. Now in the red part of the optical spectrum, I noticed a very cool star, something that's much cooler than the sun, and also something that I know from, again, detailed measurements is a giant star, something that's much larger than the sun. So these two stars seem to be composed of a very hot blue star and a very cool but very large red star. So can I learn anything more about that? Let me make one more little aside here. I think I have time to do this. So there's a famous star, also another famous star called P Cygni. The P again is a designation that it's a variable star. Cygni means it's in the constellation of Cygnus. And this was the first star that had detailed studies showing these very strange looking features. So they aren't features that just go down. They aren't just absorption dips. And they aren't features that just go up like emission features. They're features that have this shape. You can see on the right here, they have these shapes of kind of both an up part and a down part. They have a part here that's emission, and they have a part here that's absorption. And these have been known and are called P Cygni line profiles, named after the star where they were first seen. And what they tell you is that there's a very powerful, dense wind of material that's being blown off the surface of a star, heading towards you and also away from you, but you don't see the part that's moving away from you because the star blocks it from you. But the part moving towards you, you see. And so if you see a line profile, a spectral line that isn't just sticking up like emission or just pointing down like absorption, but has this shape, then you know that this star has a wind. So now we start going back to the AAVSO light curves and looking in detail at places in the spectrum, places in the light curve by looking at spectra. The top spectrum here was taken at the leftmost arrow, so you can see just past the eclipse. And you notice this absorption part right over here near 4,000. Those are those calcium H and K lines I mentioned to you before. So that's a real clue that while we see some emission lines, but not a whole lot like we did before, we also see these absorption lines. And then later on in the eclipse, which is the right arrow, you start seeing now not only do the emission lines start coming back, but if you notice, many of them have these P Cygni profiles. So you're starting to see a wind coming out of this. So you can put all this information together and you can build this really cool model, which we believe is true both for AS325 and for XX Ophiuchus. They consist of two stars. I show a diagram here on the bottom right. This diagram is to scale. So the size of the B star, that little dot, and the size of the cool giant, that orange and red dot, are to scale. And if I showed the sun on this diagram, it would be smaller than the dot that's the B star, so you wouldn't even see it. And you can see these two stars are very close together. They're orbiting around each other. They're locked in mutual gravity with each other. The B star, while it's so much smaller, is more massive and about equal in brightness to the red star, which is so much larger, but much smaller in mass and also roughly the same brightness. We also noticed in the light curve, the measurement of light over time up on the left, the eclipses aren't always the same depth. Sometimes they're deeper and sometimes they're shallower. And that's because this red star is a semi-regular variable. It changes in size from something about the size of that orange circle to something about the size of that red circle on some long period, like hundreds and hundreds of days. And so depending on how big the star is, when the eclipse occurs, gives you these different depths of eclipses. And you remember those absorption lines we saw back here, these two little absorption lines here? Those come from the B star, but it's light from the B star that shines through the outer atmosphere of the red star, and then we see it in the Earth. And when that light shines through the atmosphere of the red star, some of its light gets absorbed in the atmosphere of the red star and shows us those absorption lines. So you can study this object, and as the B star moves behind the object, it's much like a flashlight shining through the fog. You can study the details of the atmosphere of this bright red star by having the blue star's light as a probe passing through the atmosphere. It's a very fascinating system, and all done because people looked at these objects for almost 100 years. They kept observing them, and that long-term light curve gave us the clue to these. So I know I'm close to out of time, so I'd just like to conclude, and then I have some time for your questions. So the AAVSO observations are just critical to long-term studies, in particular of non-periodic variable stars at the end of their evolution, these semi-regular stars. They're not easy at all to characterize with one measurement or even measurements for a month. They need measurements over decades and decades. And it's a key to understanding these stars and understanding their evolution. Their light curve data, of course, is so valuable, and the years of it and the precision of it are just fine. And I found that forming a collaborative team is even better than just using their data. You get everybody involved in the team, and everybody gets the excitement of the mystery of that. And personally, I look forward to another 50 years of working with the AAVSO. So thanks very much. I'll stop now and I'll take some questions.
Thank you, Dr. Howell. That was excellent. All right, so let's take a look at the Q&A box. It looks like our first question comes from Robert Baker, who has asked, can you tell how fast the bubble is moving through Doppler shifts? So that would have been on the earlier star you showed, our Coronae Borealis.
Sure, that's a great question. It also would be, if you remember the three peaks we saw on our Coronae Borealis. So yeah, indeed, if you watch it over time, you'll see those spectral features actually move in position very slightly in wavelength, and that will give you information on how that shell is moving with time.
All right. Thank you. Good answer. All right, we have a question here from Timothy Weaver, who has asked, wouldn't similar odd readings in the same direction of the sky be an indication of instrument bias?
You know, it would be if it was exactly the same place, and if I only looked at each star once, say on the same night with the same instrument. But these two stars aren't really exactly in the same line of sight. And they've been studied now for decades and decades and decades by lots of people, not just me and not just the AAVSO. Well, we all see the same thing. So I think instrument bias is something to think about, but it's clearly ruled out in this case.
Thank you. We have a question here from Robert Buckheim, who has asked if you have any advice for AAVSO spectroscopists, specifically in the realm of observing cadence and spectral resolution to study these kind of stars.
Sure. So these spectra were not really super high resolution because a lot of the features you see are very broad. They're easy to see even with medium and low resolution. So my advice would be that if you're interested in certain kinds of objects, find some observers who want to do photometry, and you guys get together and do photometry and spectroscopy simultaneously. That way you'll be able to have these very good matches of when the star is bright and when the star is faint. And that's where you learn a lot, how it transitions to faint and how it transitions back to being bright.
Thank you. That's good advice. I'd like to tack on a question to that. Do you know if, in the case of these iron stars, XS Ophiuchi and the other one, would a resolution of about R400, would that be enough to get useful data for these kind of studies, or is that too low?
Yeah, 400 is a little on the low side. I think you probably have to be around 5,000 or 6,000, a resolution of 5,000 or 6,000. Certainly what you can do with 400 though, is you can make multicolored light curves from your spectrum, right? So you can take one spectrum, then measure the brightness, say in 4 or 5 bands across the optical, and you get a 4 or 5 band light curve from your spectrum.
Okay, thank you. All right, so let's see. We have another question about AS325 and XS Ophiuchi. If the variable radius, if variable radius of the cooler star in these binaries is producing different depths, does this also show in variable eclipse widths? I hope I read that correctly.
Yeah, it does. And in fact, I didn't point that out, but if you look at that light curve, and it's an AAVSO light curve, so clearly everybody can get to it, the widths also change because it's exactly right what the question was asking. The star is smaller, so the time the B star spends behind it can be from shorter to longer.
There you go. Exactly. Thank you. Okay. So we have a few questions about the R Coronae Borealis stars. So Anthony Dudden has asked, what caused the small bump at minimum in the R Coronae Borealis light curve at around Julian date? He gives the Julian date there. You can read it in the Q&A box.
Well, so these are, that's a very good question. And this is part of the interesting mystery. If you look at each of the minima in great detail, very few of them are exactly the same. Some of them, as my suspicion is of this one, some of them drop down, but come back up a little and go back down. Others go down and just back up. And my guess would be it's the density of the shell material as it's pushed out. There might be places where the shell is more or less dense, and those density blobs can cause the sort of an irregular bottom in the dip.
Thank you. Good answer. So Michael Freeberg has asked for R Coronae Borealis. How do you know that it is a binary system instead of just a variable that has a huge dip in brightness?
So R Coronae Borealis has yet to show any sort of really detailed evidence that it's a binary, R Coronae Borealis, right? However, theoretically, and with some hints from long-term radio velocity measurements, there is a hint and a belief from theory that it probably should be a binary. And myself and others have looked in great detail to try to show if it's a binary or not. And the best we can guess is if it is, its companion is probably a white dwarf, and it's almost impossible to detect it is the problem. Mm-hmm. So indeed it could be, but so far I don't believe there's any direct proof that it is, other than we all kind of suspect it.
Okay, thank you. Another question about R Coronae Borealis stars. This one comes from Franz Joseph Hempsch, who has asked if you have also looked at hot R Coronae Borealis stars, such as V348 Sagittarius.
You know, I have a little bit, but I haven't looked at them in as much detail as I've looked at the cooler ones. But those objects are fascinating as well, so people should do them. Yeah.
Great. Michael Poxon has asked if there is any maser emission from the R Coronae Borealis shells.
Yeah, I don't think anyone's detected that yet. There is certainly maser emission from some of the very largest, coolest supergiant stars and big giants, but I don't think anyone's seen maser emission from our Coronae Borealis.
Jay Miller has asked, what spectrographs were you using to get the high resolution spectra?
Yeah, so those spectra came from 3 different spectrographs. The majority of them came from Kitt Peak National Observatory on their 2-meter telescope when that was still in use. Some of the other ones came from the Gemini Observatory, both north and south.
Okay. Thank you. Robert Baker had a question. He asked, can you see evidence of magnetic fields and do the spectral lines split?
That's a great question. So I think he's talking about the phenomenon called Zeeman splitting. Zeeman splitting has not been seen as far as I know. You really need high resolution spectra to see that. So I wouldn't see it in my spectra. There have been studies of polarization where people look for dust grains that get aligned with magnetic fields. And there is evidence from there that there are weak magnetic fields, at least in the shells and the atmospheres of these stars that do align the dust grains. But those would be magnetic fields that are sort of the level of the sun's magnetic field, or maybe a bit stronger, but probably not strong enough to get this Zeeman splitting of the lines.
Okay, thank you. Good answer. Michael Poxon had another question and asked, he's heard that several R Coronae Borealis stars show quasi-Cepheid pulsation. Is that true? If so, why do they show this pulsation?
I've heard that too. I believe it's true. And why is a great question. We should investigate that.
All right. Thank you. Jean Malone has asked if there's any chance of making RV measurements in R Coronae Borealis and the iron stars to get mass functions. I'm not quite sure what RV stands for there. Radial velocity? I don't know.
Yeah. Hi, Jean. Nice to have you here. So they've been looked at, as I said, in a lot of detail with spectroscopy to mostly see, for example, if they are binaries, because you would see the spectral lines go back and forth. And I don't believe that anyone's done a great job yet, or even noticed any radial velocity motion in our core bore that's going to lead to a binary. And certainly in our Scuti, I believe it's pretty confirmed that star is a single star.
Okay, thank you. Mercedes Correa had a question. He asked if P Cygni profiles can be observed in novae.
Absolutely. Yep. Yeah, P Cygni profiles are observed in anything that has an ejected shell or wind or whatever. You can even see them in supernovae.
Thank you. That looks like that's the end of the questions for now. So thank you for your presentation. It was very enlightening. Now I'm going to introduce our next presenter.
Hey, thanks, Lauren. Thanks, everybody.
Thanks, Dr. Howell. All right, our next presenter is an expert researcher in the field of cataclysmic variables with over 50 peer-reviewed publications on the topic. He's worked closely with the AAVSO for decades, collaborating with our observers to try and detect dwarf novae during the early stages of outburst. Today, he'll be sharing with us some data on one fascinating dwarf nova in particular, DW Cancri. Ladies and gentlemen, please give a warm welcome to Dr. Juan Echevarría. Dr. Echevarría?
Okay, yeah. Hello, good afternoon, or whatever time you are in. My name is Juan Echevarría, as Lauren said, and she didn't mention a piece of my curriculum vitae, which I think is pertinent now that I was listening to Steve talk. And the thing is that I became an amateur astronomer when I was 13 years old, 13. So that's more than 50 years ago, okay? And since then, I pursued the idea that I could become a professional astronomer, and I did. I went to England to do my PhD, and when I came back to Mexico, I started collaborating with the AAVSO in an international campaign to detect dwarf novae during the rise to the outburst. Okay, let me show you one of the highlights that the AAVSO is very proud of, and it's can you see the?
Not yet.
No.
No. Here, I can invite you to share your screen, I think. Well, okay, so down at the very bottom of your screen, there should be a toolbar with a green share screen button. Are you able to click on that? Should be at the bottom of your Zoom window. There you go. Now you can see it.
Yeah. Okay. Excellent. So this is a graph that was published by Warner in 1992 in his very large Bible about cataclysmic variables. And you can see that SS Cygni, one of the brightest CVs, has been followed by the AAVSO since 1896 up to date. Right now, by the way, it's doing a very funny thing. It had never done it before, but thanks to you, the observers, we have detected that the object is in standstill. So this is just an example how valuable the contribution from the AAVSO is. When I mentioned about my early fascination with astronomy, it's just to encourage some of you that you could, if you wish, become a professional astronomer. And there is no limit at which you can start switching from amateur observations to professional observations, okay? Now, what I'm going to do is to show you a presentation on a specific object, DW Cancri. Instead of talking about cataclysmic variables in general, I would like you to know or to see an example of what a professional astronomer has to do to start a program and how it ends, no? And I am showing here you the end of the research in a paper that was published in Monthly Notices in 2020. And you see that my name is last because this was the MSc thesis of Omar Segura. Okay, so he got his MSc from this paper, and you can see that it's something very very precise. You have to, everything that you say in your paper has to be supported by references and logic statements. Okay, so this is what it looks at the end. But I'm not going to just go through the paper. Instead, what I'm going to do is to show you a hold on. I don't know why it's showing. Do you see only half of the graph?
Right now, we're seeing your presenter's view. It's got the slide on the right and the notes on the left.
Yeah, I want to take out the notes.
Okay. Do you know? Yeah, that button. Good job.
That's it. Okay. So what I'm going to present you here is a modified talk that I gave more than a year ago in Armenia in a meeting about white dwarfs in binary stars. And this presentation was attended by Stella Kafka, your president, which I have seen several times in astronomical meetings. So I decided to do this because I want you to, as I said, I want you to follow what do we think first about doing on an object, and how do we proceed stage by stage. So what we did was a spectroscopic study of this 86-minute orbital period intermediate polar DW Cancri. And to date, to the time that we published these observations, no derivations of the masses and inclination angle were known. At least they were poorly known about these dwarf novae. And we show in this presentation that the 86-minute signal, which is associated with the orbital period, is very evident in our radial velocity analysis. But we don't see another signal that should be present, which is a 39-minute signal, which is associated with a white dwarf in the system. Do I need to explain what is a cataclysmic variable? I don't think so. I think that most of you will know the basics about CVs. However, just to be on the safe side, this is a artistic picture of a CV. And here you can see several things. One is that in this very bright spot, you have a white dwarf. That's a degenerate star, and we call it the primary star. The secondary star is a late type star, a K or perhaps an M star, which is filling its Roche lobe, which means that the outside the surface of the star is in such a condition that is starting to transfer mass towards the white dwarf. And this starts a process of accretion into the white dwarf. When the disk is well formed, the matter strikes at the outside rim of the disk and produces a bright spot. Now, this is the classical model that was developed by Werner and Nader and by Smack, both in 1971. So they both teams deserve the credit to have solved the puzzle of cataclysmic variables, which now we know that nova, novae, and dwarf novae and nova-like objects are all of the same kind of objects. A white dwarf primary is a late type secondary filling its Roche lobe, accreting matter towards the white dwarf. But what happens if the primary star has a very strong magnetic field? Well, the lines of the bipolar magnetic field inhibits the formation of an accretion disk. So the matter that is being transferred into the gravitational well of the white dwarf cannot form a disk, but eventually it goes through one or both magnetic poles of the white dwarf. And there is another intermediate kind of system, one which has a magnetic field in the white dwarf, but it is not so strong, so that the material going into the white dwarf can form an external disk, sort of a ring. But when it starts to get closer to the white dwarf, it will stop being able to form a disk, and instead the material has to go through one or two of the magnetic poles. And this is what we call the intermediate polar type. The polar systems are those who have a very strong magnetic field, like this. These have no strong magnetic fields in the white dwarf, and these have an intermediate field. Okay, so this is your contribution to this work, which consists of almost 20 years of observations. Here I just plotted from a standard Julian day 3000 and plus that number in the bottom. And this graph takes about 16 years of observations, but we have, I will show you another one with further AAVSO observations. And you can see that our spectroscopic observations were taken when the system was at this point. That's to say that the system, for the first time in many, many, many years, it started to decline. It went into a low state. Unfortunately, we did not get this part of the system, but we got when it was going down. And I will show you at the end when the system recovered and went back into a high state. Okay? So lots of information that you have provided to us, and this crucial part is the one that has enabled us to make an explanation of why we have observed a substantial change in the modes of processing of the signal emissions. This is just to show you one of the many spectra that we took with a medium resolution spectrograph at the San Pedro Martir Observatory. On the right, you see the typical H-alpha line, and this is a helium-1 line, 5876 angstroms. So we made an analysis of both lines. Now, I have to mention that because this is a very short orbital period system, you cannot see the secondary star. The secondary star is too small, and therefore it's almost invisible to us because the accretion disk is dominating the light and you cannot see it. You can see it in other systems like SS Cygni, which has about 6.5 hour orbital period, and you see both the emission and the absorption line systems. This is just a blow up of the H-alpha line, just to show you that we detected that the line has a double peak. This is just a summary of the observations. The observations were made mainly in 2017 along 5 or 6 days in January. Okay, and we observed a total of 465 spectra, each one with an exposure time of 300 seconds. Now, let me also mention that the system is very faint. This is a system that here in this graph, you see that the magnitude of the system is about 15.5 in the visual. And when it goes down, it goes to about 17.5. That's about 2 magnitudes fainter. So this is a difficult system to observe, even for amateur observers. You have to have a good telescope, a good size telescope in order to catch it at this low state. Okay, so what we did was to approach measuring the radial velocities of the lines using a Gaussian method derived by Schafter, Scuti, and Horn, and a diagnostic diagram that allows you to select what is the best separation of 2 Gaussians and what is the best width of the Gaussians to get the best results. This is a very technical thing, but it has to be done in order for the rest of the community to believe your results, okay? So I'm showing you here an example of such a diagnostic diagram in which you run with a given width of the 2 Gaussians, you run a program changing the separation of the Gaussians, and you expect this index, which is sigma over k, which is k is the semi-amplitude of the line, and k is the error. And you see that in this way, you get a minimum about here, and this is where you get the best result. So you have only to extrapolate this result to see what is your best semi-amplitude of the radial velocity. So this is the way, the technical way to do it. And these are the results with the best solution. And you see very clearly that you see a very nice radial velocity curve with the 465 spectra. And we see only a variation with the orbital period and not with another signal like the spin cycle of the white dwarf, which I remind you is 39 minutes compared with 86. Okay, now you wonder perhaps why we are fitting a sinusoidal curve to the data. And the reason is that in these closed systems, the tidal forces in the binary, because the 2 stars are too close to each other, that eccentricities are dissipated out, and there is no way that you can keep a system at this short distance being eccentric. So most, or I would say all CBs have circular orbits, okay? In this way, it's easier to derive the orbital parameters because you will only have to fit 4 parameters instead of 6. But also, we have a way to, instead of fitting 4 parameters, we fit only 3 parameters. Why and how? Well, let me, okay. So first of all, we don't see the modulation of the spin, nor do we see another frequency, which is the beat period, which is a combination of the spin period and the orbital period, okay? So we don't see a spin modulation in the radial velocity curve. So far, we have that we can derive the 4 orbital parameters, but I was going to say that first, and I'm going to show you this in a second. First, we derived the orbital period using a power spectrum analysis on the radial velocity spectra, okay? So what we do is when we run the calculations, we keep the orbital period fixed at that value of 86.005 minutes with a very small error. Okay, so what's the problem? We don't see the 39 minutes, but it happens that this object was observed by Joe Patterson, which I'm sure many of you know. He runs the Center for Backyard Astrophysics program, and he observed this object in 2004 and found the 39-minute signal as well as the beat period. So let's see what did Patterson and also Rodriguez et al. Found. Well, you see clearly here that from the photometric observations, you see a very nice fit, both near the orbital phase, which is on the lower right panel. You see the 38-minute phase, which is the spin phase of the white dwarf. And also, this is the beat period. The 70-minute phase is just a combination, a mathematical, let's say, combination, a natural period that appears when you have a system that is revolving with two frequencies or two periods of orbiting or presenting. Also, they show a 110-minute phase periodicity, but they are not able to explain why this is so. So they leave it aside. But they also did spectroscopy, and you see in the upper right panel, you see that the light curve, the radial velocity, curve is very very mixed, confused. It's not like what we observe here. It's a very clear signal with no noise. Well, it's just the intrinsic noise of individual spectra. But what Patterson observed was a sort of a very noisy radial velocity curve. So what he did, he and his collaborators, was, okay, let's fold the spectra with the short period, that's the spin period, and still he gets a good result, but still it's a bit noisy. So what he does is, by looking at the power spectrum of both signals, he cleans somehow both signals, and here you see a very clean long period, which is the orbital period, and also the short period. And we were not able to see this. We tried to fold it with the spin period, and we were not able to do it, okay? So this is the kind of power spectrum that you do. This is the spin period, this is the beat period, and you see that the orbital period has a very small power compared with the other signals, okay? So what they see, and also Rodriguez et al. In the same year, they published simultaneously the results. They see that the main source of the periodicity comes from the spin period. Secondly, from the beat period. And thirdly, and very faintly, from the orbital period. But our results show that the orbital period, which is shown in the top graph, has a strength much much stronger, than the beat period, and for the spin period, you see nothing, okay? So we were not able to detect even by 0.5 strength in theta, the spin period. So we said, okay, perhaps what we're doing wrong or different from Patterson and collaborators is that we used the wing method to measure the radial velocity of H alpha. So we decided that we were going to do a simulation in which, with the program that we use, you can fit a single Gaussian instead of two Gaussians, and this is called the D-Gau option. And then the routine that we use is in IRAF. It's called the convolve RB routine. And then you also have to allow for the best result. And here are the results that we got. We see now a better signal here at the beat period and a small contribution from the spin period. But still, it's very weak. So something changed. Even with using a simulation of his method, of their method, something changed substantially. We almost, I must conclude, we almost do not see in these observations the spin period of the white dwarf. So the spin period is detected, but it's very, very weak. So we wonder why was this change, and we found that the reason that we could argue was precisely on this graph. The reason was that the system has gone into a low state. And when the system goes into a low state, the mass transfer from the secondary star is inhibited. So mass transfer stops a bit or enough for the matter not to jump into the internal part of the, hold on, to the internal part of the system. That's the material will not jump into the white dwarf. That's why we don't see the spin period, okay? And this was accepted, of course, by the referee as the explanation. And it clearly shows that the matter will not jump into the inner part of the white dwarf region, and therefore we will not see the spin period. Okay, well, if we are correct, then we expect that when the system goes back into a high state, then we will recover the signals, the 39-minute signal, and also the beat period. And you see here on your right that I have included observations by the AAVSO after our observation. So we said, okay, the system has gone back to a high state. So now we can go back and observe it again. And we should now recover the three signals, okay? So, well, this was the explanation I've just given to you. We did also a reconstruction of the H alpha line and the helium-2 line in a method called Doppler tomography. This is a very complicated procedure, but somehow you recover the disk that is producing the emission line. But here you have just to take into account that what you see in your left here, this is an image which is not in geometrical axis, but instead on velocity axis. Okay, this is very important because in this image you will see that the low regions, that's regions that are close to the white dwarf, have low velocities. That means that these parts of the image are the outside parts of the accretion disk, while the outside parts, including the blue part, are regions which have a large velocity. So these are the parts that are closer to the white dwarf, okay? Because in the accretion disk, you have a relation. The outside parts of the matter at the rim have a low Keplerian velocity. And when they start going inside the white dwarf, they keep a Keplerian motion, and therefore they start going faster, okay? So this is just a complicated thing. And I'm sure that you can read it in a few articles about this complicated technique, okay? This is an image of the helium-1 line, and we see some sort of spiral arm structure, but we're not completely sure that this is real, no? Okay, so what now? Well, as I mentioned, the system went back to a high state, which is shown here. And in March 2020, which is now a year ago, before the observatory was closed due to the pandemic, we were able to secure a few observations, only 4 nights of observations. But this time we did 4 nights with photometry in one of the telescopes, and we did only 2 nights spectroscopy. And the reason was that the weather was very bad, okay? So I'm going to show you now. I have not prepared this into a PowerPoint presentation. So what I'm going to show you is just a draft of a new paper that we are preparing based on the observations done on March 2020. This is just a draft, and now what you see is the starting of another paper, but now not the final version, like I show you at the beginning of the talk, but this is just a first draft, and we are little by little including more data, observations, and results and interpretation. Here are the observations made on those days in March, 4 days. We did V and R photometry, okay? And we did spectroscopy only on the 16th of March. And these are the results, again, using the wing method to derive the parameters of H alpha, and also these are the results for the helium-1 line. But now, the interesting thing is, now we did a power spectrum search, first on the photometry, which we did not have at the beginning in the first paper. And here you see that in both the V band and the R band, you see a very clear frequency, which is associated with the spin period. And just collecting both V and R observations, you get a better, perhaps a better result, okay, of 37.47 cycles per day. And here we have folded the observations. We have just combined the V and R observations by shifting by a quantity, a reasonable quantity, just for you to be able to see that the results are the same in the V and R, and you see clearly the modulation by the spin period. So these observations are folded with the spin period. And in the bottom, you see the observations folded with the orbital period. And in the orbital period, you see absolutely no modulation. However, if you do the same with the radial velocity observations, then what you see is the orbital frequency, not the spin period frequency. This frequency is associated with the orbital frequency. And just for you to be convinced, here is a graph that we have to make it better because we did not shift properly the H alpha and helium-1 solutions. You see that there is a very nice result with the orbital phase, while if you do the same now for the spin period, there is nothing. So, in conclusion, when we observe, sorry, I have to switch something on. So in conclusion, in March 2020, the object, although it was back in a high state, has not still recovered the full properties observed by Patterson et al. And by Rodriguez et al. Now, I will not tell you the results of a new campaign because we were able to observe, although San Pedro Martir was closed, we were able to observe with a spectrograph in another observatory in Cananea in Sonora in Mexico. And we have more observations of this system. And now we hope that once we start reducing the data, we will see a full recovery of the system. So this is just to show you the way that we deal with an idea, with a program, with starting to observe an object, how we proceed, how we compared with previous observations, how we published a full paper, and how you continue to observe the system, hoping that your predictions will come true. And that's it. Thank you.
Thank you, Dr. Echevarría. All right, let's go ahead and take some questions. So it looks like our first question comes from Hasib Saib, who would like to know if you are open to mentoring someone who is in South Africa.
Sorry, I did not understand the question.
Are you open to mentoring people, was the question.
Oh, yes.
All right. Well, in that case, I'm going to say to Hasib that you should reach out to Dr. Echevarría offline.
Yeah, sure. You're in South Africa, you said?
Yes, that's what it said.
lovely country. And I gave a talk in Cape Town several years ago, but I wasn't able to observe with the 2.5 meter telescope in South Africa.
All right. Let's see. Has anyone else got any other questions? The remaining questions that I see here in the question and answer box are compliments on an excellent presentation. Anyone else? Okay, Hasib has asked how best to get in touch with you.
Okay, well, write to me to my email, and do you have my email, Lauren? Can you?
Yes, I do. I can put that into the.
That's the best and quickest way to reach me, by email. Later on, if you are interested, we can switch to Zoom conversations and whatever.
I'm going to go ahead and type your email out as a written reply so that people will be able to see it. And in the meantime, if anyone else has any other questions, please submit them. Otherwise, we'll just go straight to the closing. Okay, now if you go to the question and answer box and tab over to the answered tab, you will be able to see Dr. Echevarria's email address. Okay, I think that's it. I think that's a sign of a well-explained presentation. So thank you very much for your presentation, Dr. Echevarria.
Thank you.
I'd also like to give a big thank you to Dr. Howell for his excellent presentation earlier. And also thank again our sponsors. For that, I'm going to go ahead and share my screen, which may end your screen share. Just a warning there. Come on. There we go. That should kick in. Okay. Now, I would like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Today's webinar has been recorded, and the recording will be made available for free on the AAVSO's YouTube channel, where you can find a full library of recordings just like these. Go check it out, and while you're there, consider subscribing to our channel. Not only will you get notified every time a new lecture is posted, but by hitting that little subscribe button, you'll be increasing our educational reach and making YouTube more likely to suggest our videos to others. It's just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So please, if you're not a member, join the AAVSO. AAVSO membership comes with a wide array of benefits, including free access to our mentorship program. So if you want to become an observer and check out perhaps some of those cool iron stars that Dr. Howell was discussing, but you're really not sure where to start, our mentors can help you. So check out our mentorship program. And if you're already an AAVSO member, don't forget to renew your membership so you keep access. Of course, we would be grateful if you would consider donating to the AAVSO. Every donation matters and goes towards making programs like this come to life. One last thing before you go. After you leave the webinar, you will be automatically directed to a survey. Please do fill it out, even if you've already filled one out in the past, because we want to hear your feedback and we review the survey results after every webinar to make some plans that will shape the future of the webinar series. Do note that the survey is anonymous, so if you use it to ask any questions that you want to receive a direct reply to, make sure that you write down your email address in the text box at the bottom. Finally, I'd like to extend one last huge thank you to both Dr. Howell and Dr. Echevarria from all of us at the AAVSO. We appreciate you.